like treating calcium fluoride with hydrogen oxalate ion rather than oxalic acid, or treating calcium fluoride with oxalic acid along with hydronium ion. Remember those questions? Key will be up this afternoon, as usual, regarding questions that you may have about any quiz. You first look at the key, second you consult your discussion instructor, and at last, as necessary, see me. Since I am they. I say that because oftentimes students come into my office with a past quiz or exam telling me about what they want. I'm they. I wrote all those questions, every one of them, as I have told you. Every quiz, every exam that I give in this class is an original invention. I don't repeat using quizzes and exams from past times that I've taught this. That makes me stale. I don't want that. This is too much fun to sit down and not think about it. The fun part comes in the thinking about it. And as I have announced previously, tomorrow I get the repair surgery on this unfortunate muscle tear that I have, commonly known as a hernia. If possible, I'll be here on Friday, but I have no idea how much pain or agony I will be in for a period of time following the repair. I go to the surgical pavilion tomorrow at North Florida at noon, and I get out at 4 o'clock. Pretty good. So if things go according to my plan, about 7 p.m. tomorrow, as usual, I'll have my shower, and then my vodka, and then my dinner. In that order. And I'll be here on Friday. Now, if I'm not able to perform on Friday, Mr. Mosen will fill in and do quite a creditable job. He's done this for me on a number of occasions in the past, for which I am quite grateful.
Hey, Mr. Mosen's my dad.
Mr. Mosen? All right, Professor Mosen. How's that? We'll elevate it. Now then, the last topic of sorts in Chapter 19 on equilibrium analysis, aqueous solutions of semi-soluble salts, which is really a topic we've already been involved with. Alteration of solubility by chemical methods. Because when we've considered, for example, the solubility of calcium carbonate in water solutions that are buffered at pH 8 or 6, that's a chemical method which affects solubility. When you talk about lacing a solution with silver ion, and then observing the solubility of silver chloride in the silver ion lace solution, or chloride ion lace solution, that's a chemical method. So we really have already done this. So when I rewrite these notes, I'll change this title. So what? But in this last section E, we will soon be discussing the formation of complex ions as a way by which to affect the solubility of semi-soluble salts. And in so doing, by demonstration, consider some of the work that you folks will do in 46 laboratory. Maybe you've already done it, but I don't know that anybody is so far along as yet to be near the completion of assignment 6. Take a look at the important statement that you see in bold on page 1913. The statement, in essence, says, if I observe the solubility of a semi-soluble salt in water solution, which contains an acid stronger than water, and the semi-soluble salt is composed of a base that's stronger than water, the solubility of the salt must be greater in the acidic solution than it is in straight water. Why? Because the acid will attack the base component of the semi-soluble salt more effectively as an acid than does water. With an exception. That's what the statement's about. If the acid in the acidic solution is a precipitator of the salt, then the salt will be less soluble in the acidic solution than it is in straight water.
What if the acid contains the anion, like...
The acid does contain the anion. That's why it will be a precipitator of the salt.
Okay.
That's what we're going to now look at. Example, gypsum. Solubility in straight water we've already recognized to be determinable by square root of KSP because of the very, very weak base strength of sulfate ion. Hydrolysis need not be considered. Or on considering hydrolysis for sulfate ion, you find out that practically speaking, hydrolysis extent is nothing. So the solubility in water is KSP square root. There it is. But what about the solubility of calcium sulfate in 1.0 molar sodium hydrogen sulfate solution? 1.0 molar sodium hydrogen sulfate solution has a pH of 1.0. 1.00 in fact. The arithmetic on the board shows that. The hydronium ion molarity in this solution is 0.10, for which the pH is 1.00. A solution which is 1 million times more acidic than pure water. Will the solubility of calcium sulfate be increased relative to its solubility in pure water if I take the calcium sulfate and treat it with the sodium hydrogen sulfate solution? Answer, no. The solubility will be decreased because hydrogen sulfate ion is a source of sulfate ion, and that's what you need to make calcium sulfate. The proof is on the board. First, for the 1.0 molar sodium hydrogen sulfate, with K hydrogen sulfate ion, we determine the hydronium ion molarity as well as the sulfate ion molarity by this recipe, which we've used many times previously, to find out sulfate ion molarity as well as the hydronium ion molarity is 0.10. So, if I look at the equilibrium established by saturating the sodium hydrogen sulfate 1 molar solution with calcium sulfate, as usual, the calcium ion molarity will be the same as S, but now the sulfate ion molarity is 0.10 plus S, because I got two sources of sulfate ion now. The dissolving of calcium sulfate plus the sulfate ion put into the solution by the ionization of hydrogen sulfate ion. At a glance, you should realize that in this system, the value for S, which has got to be smaller than this, cannot add to 0.10 and make 0.10 become a larger number. So in doing the arithmetic, we find simply that the solubility, which is the calcium ion molarity, is KSP divided by 0.10. There it is. And that's a good deal smaller than 3.0 times 10 to minus 3. Why is the solubility smaller? As we've already noted, because hydrogen sulfate ion is a precipitator of calcium sulfate. If you, for example, were to try to up the solubility of copper sulfide or silver sulfide by treating with hydrogen sulfide, given that hydrogen sulfide is a much stronger acid than water, you decrease the solubility, not increase, because hydrogen sulfide is a source of sulfide ion, a precipitator of sulfides. Now then, let's take a look once again at our favorite stuff. Certainly my favorite stuff. Calcium carbonate and its solubility in 1 molar ammonium chloride solution. What have we looked at so far? Calcium carbonate solubility straight water, where we found the solubility of 1.4 times 10 to the minus 4, after paying attention to the equilibrium established by dissolving calcium carbonate, the dissociation equilibrium, in conjunction with Kb carbonate ion. Or the solubility in water solution buffered at pH 8 or water solution buffered at pH 6. I've written the value for the solubility at pH 8, which is in the notes and which we did in class a couple gatherings ago. 1.1 times 10 to the minus 3. Can we say matter-of-factly that the solubility of calcium carbonate in the 1 molar ammonium chloride solution has got to be bigger than 1.4 times 10 to the minus 4 molar? Before we do any arithmetic. Is this solution more acidic? Is this solution more acidic than straight water? Is ammonium ion a stronger acid than straight water? Yes. A good deal stronger acid than straight water. And neither ammonium ion nor chloride ion is a precipitator of calcium carbonate. Hardly could be. So, we know the solubility of calcium carbonate on treatment with the ammonium chloride solution has got to increase relative to the solubility that it exhibits in straight water. It will also increase to some extent by the salt effect. But the chemical effect is much greater than the salt effect, so we'll forget the salt effect for this analysis. And we'll also ask the question at the start of this analysis, can we expect the solubility of calcium carbonate in a 1.0 molar ammonium chloride solution to exceed 1.1 times 10 to the minus 3 molar? This is the solubility at pH 8. What simple experiment would you do in the laboratory to answer this question? Will the solubility of calcium carbonate in the ammonium chloride solution be larger than or smaller than 1.1 times 10 to the minus 3 molar, which again is the calcium carbonate solubility in water solution buffered at pH 8? What simple experiment would you do in the lab? We get the answer to this question. Not calculation, experiment.
You can add calcium carbonate to water and know what you started with.
Don't need to do that. We've already done that.
And then you know how much you get out as a precipitate. And then you can...
You're adding calcium carbonate to the wrong stuff. We've already done the calcium carbonate in water.
You do the same thing with the ammonium chloride.
Don't tell me same thing. Tell me specifically what.
Add set amount of calcium carbonate.
Set amount. We don't need a set amount. Add calcium carbonate to 1.0 molar ammonium chloride solution until you observe what?
Precipitation.
You won't observe precipitation. You will observe no further dissolving. Okay? You're going to make saturated calcium carbonate solution in the ammonium chloride solution. Okay so far? Then what?
Then you're going to continue to add, right?
I want to know what you're going to do now. You're in 46 laboratory.
Test the pH.
We could do what?
Test the pH.
Louder.
Test the pH.
Louder. They can't hear you. Observe pH. Because if I find the pH to be less than 8, what conclusion may I reach? Will the solubility be bigger than 1.1 times 10 to the minus 3 molar or smaller? Bigger! Yup! Isn't pH, if I get a pH that's less than 8.00, is not this saturated ammonium chloride calcium carbonate system more acidic? Enough said. It's more acidic, carbonate ion is destroyed more effectively. Solubility, beep, upped. Greater than exhibited in pH 8 buffer. And that's what you'd find. Now I've tried to do this in class by experiment and demonstration, but I've had difficulty getting good results with our student grade pH meters. So I'm going to order a research grade pH meter and go further with this. That'll probably cost about $1,000. I don't give a damn. for the purpose of education. It's well worth it. And for reasons which frankly I am not quite sure about, but which I'm happy about, I'm the guy who's more or less in charge of spending the money that's collected from laboratory fees for general chemistry. Now you folks pay very tiny laboratory fees for general chemistry. I think it's about $10 a student. But we have many of you. So I'm sitting on about 49,000 K. And what do I use it for? Things like this. You know, that's all. That's how I bought this microphone and microphone camera to make these video recordings. Hey, $800 and I can put all this stuff online on the internet. UF has spent over $100,000 on doing the very same thing, and they can't do this successfully. I don't know what the hell they're doing. I worked with them one time, and they had this process so fouled up it was horrid. Never again. No way. It's going to be done my way, or not at all if it's going to be done by me. Because as you know, UF is doing a lot of let's go online with stuff. I'll be glad to teach this class online, but I'm not going to talk to a chalkboard. If I teach this class online, it's going to be with a live audience. It's going to be done directly from my 2046 class. And it's going to be done my way with my people recording the presentation and putting it on the internet so everybody in the world who wants to see it can see it. And if they don't like it, I ain't doing it. That's the end of it. And notice, that ain't is a word usable only by emperors and empresses of Byzantium and chemistry instructors. Any emperors or empresses of Byzantium in here? I didn't think so. One time I asked that, one guy stood up. I says, "Where the hell's your crown?" He sat down. See, he lied. But it was worth a laugh. In any case, equilibrium established. Equilibrium constant. The multiplier is necessary to allow us to evaluate K for this equilibrium constant. Becomes a composite of this times this divided by this. Could I have achieved this by multiplying by hydronium ion molarity over hydronium ion molarity rather than hydroxide ion molarity over hydroxide ion molarity? You're damn right. What would I have then? I'd have a composite of Ka ammonium ion and Ka bicarb ion. Anything that you do works. It's never going to give you a different K value. An equilibrium reaction at a given temperature has one single K value, period. That's why it's called a constant. I put in the numbers, grind, I get 7.2 times 10 to the minus 8. Is calcium carbonate particularly soluble in ammonium ion? See that K value? That K value is very small. So we know we're not going to up the solubility considerably. But we know the solubility is greater than it is in pure water, but because when we wrote the calcium carbonate plus water equilibrium reaction, do you remember that we got a K of 1.3 times 10 to the minus 12? So that, by calculation, would establish that the calcium carbonate is certainly more soluble in the ammonium ion presence than it is in straight water. Now, I want you to change or simply strike question 1915 as it appears in the notes and replace it with this version or with this question. I'm going to call this the new question 1950. So for the text that you see in Chem Notes on page 1915, practically speaking, forget that text. So now you're just going to have to pay attention to what we do with this analysis right here and now. We are posing the question, can I correctly calculate the solubility for calcium carbonate saturated in the ammonium chloride solution without material balance or charge balance considerations? Well, before we tackle this, let's have a little vote fun. How many think we can do this? How many think we know we got to have charge balance and material balance? Now I'll ask the dirty question. Who didn't vote? 2 million points off from yesterday's quiz. So when you see your quiz score posted, it'll be whatever you made less 2 million. So you're going to see a big negative number in at your data point. I'm rotten. Ooh. Now then, question. To what extent may we expect carbonate ion to react with ammonium ion when this equilibrium is established? Remember when carbonate ion and calcium carbonate reacted with water, 70% of the carbonate ion converted to bicarb and hydroxide ion, 30% stayed back. What can we say about the extent to which carbonate ion converts to bicarb ion by this reaction? Larger, for sure. Because this is a stronger acid. What are you going to tell me about the extent of this reaction? On what basis do you say large? You're correct. Remember our rule of thumb for getting at extents? This acid, stronger than this acid. Reacting acid, stronger than product acid. This base, in turn, stronger than the product base. So without any calculation, we expect this reaction to be large extent. When calcium carbonate was saturated in water, did carbonate ion react to a large extent? When calcium carbonate was saturated in water, did the carbonate ion component of the calcium carbonate react to a large extent? No. To what extent did it convert? 70%. Damn it, isn't that large? You got to think about this stuff. Remember, the molarity of calcium carbonate in water is pretty small, right? Dilute, right? And Kb, 2.1 times 10 to minus 4, that's Kb carbonate, is a lot bigger than 1 times 10 to minus 7. Does that sound like it then goes to a large extent? Does this sound like a question I asked you about on yesterday's quiz? Huh? Like the last question? You remember that? Different molarities of hydrogen sulfate ion. Remember that? All about what we just said. Except that one of the hydrogen sulfate ion solutions was so damn dilute that in addition to 100% hydrolysis, what else did you have to consider?
Autoionization.
Autoionization of? Water. Bingo. And that's what I'm looking for you. I mean, looking and hoping that you told me regarding your response to that on yesterday's quiz. Because what I'm going after all the time is, do you or do you not understand this stuff? Because if you go through this course and try to get at it successfully by looking for formulas in which to jam numbers like you did in 2045, forget it. That stuff is gone. We're doing real chemistry which is premised exclusively and entirely on understanding. There has to be. And on we go. Next question. Given that carbonate ion by itself with water reacts to a small extent, but calcium carbonate in water results in carbonate ion conversion to bicarb to a large extent, 70%. This number tells us 7.2 times 10 to minus 8. That this is not an effective way to dissolve calcium carbonate. That means the calcium carbonate molarity in this system will be small or large? Small or large? The calcium carbonate solubility. Small or large? Small. So M sub I will be small. And we're still talking about carbonate ion, but now it's reacting with an acid, which in and of itself will react with the carbonate ion to a large extent. So is it fair to believe that in this system there will be no residual carbonate ion of consequence? Is it fair to believe that all the carbonate ion will go away? Let's repeat the results of our lab experiment, where we find that saturated calcium carbonate and ammonium chloride system gives a pH lower than this. At this pH, did we have any carbonate ion in solution that amounted to anything? And this solution is more acidic. Is there going to be any carbonate ion in this system? Hell no. So we can take this as, practically speaking, a 100% reaction. We're just paying attention to information that we have available. Now, next question. You think this reaction will go in this system to an extent which must be considered? Yes or no?
Yeah.
Why?
It's acidic.
Not enough. Do you remember back in chapter 17? Or did I talk about that in chapter 18? It was chapter 18. The gang up factor? Remember the gang up factor? Remember my story about Muhammad Ali? Remember that? You don't remember the story about Muhammad Ali? How many of you know who Muhammad Ali is? I'm not much of a fan of pugilism, but I like watching that guy. There was a great deal of truth in what he said. Float like a butterfly, sting like a bee. It was very good. And I venture to say that when he was in his prime, he was the best heavyweight prize fighter that ever did this thing, pugilism. Well, when he was in his prime, would any one of us like to have jumped in the ring with him and went like this here? What would have happened? Kapow, we're gone. But if the whole damn bunch of us jump in there, 70 or 80 of us might get murdered along the way, but eventually we'd overpower him by the gang-up factor. In this system, is bicarb ion being ganged up on by ammonium ion? This is 1 molar ammonium ion, right? The ammonium ion molarity is high. And we've already reckoned that the calcium carbonate solubility is not great at all. So whatever the bicarb molarity is developed by that equilibrium, and it can't be very high. So this corresponds to a gang-up factor reaction. Does that offer us the opportunity by this ganging up on this to convert some of this to this? Yes or no? Yes. Of course. Now, even though gee whiz analysis tells us this is a small extent reaction, right? Because this acid is a good deal stronger than this acid, and this base is a good deal stronger than this base. By the gang-up factor, we can still expect a reasonable degree of conversion. Well, if that's true, when we return to this equilibrium, what do you think about the prospects of calcium ion molarity, bicarb molarity, and ammonium molarity all being the same? Do Do you think they might be the same within the limits of significant figures? Possible. And if they are the same within the limits of significant figures, then guess what? The answer to this question is yes. Now let's find out. Let's do the calculation. Because we've recognized in this system, carbonate ion is going to disappear entirely. Which means at the minimum, all the carbonate ion becomes bicarb ion. The second part of the puzzle is, will some of the bicarb ion convert to this? Well, we've said that based on the gang-up factor, that's a possibility. Well, let's get on with the analysis. The analysis at this point being based on taking the molarities of these things to be the same. Now, before we get on with the arithmetic, let me ask one more question. Do you believe in this system that the only way by which ammonium ion converts to ammonia is as a consequence of its reaction with calcium carbonate in this system? Now notice, if this goes to any measurable extent, that this also produces ammonia. So we've looked at this as a source of ammonia. Clearly it is. This is a possible source of ammonia. We don't know for sure. Is there any other possible source of ammonia production in this system? What do you mean water? Reaction with water. Not water. Be specific. Water. Damn good too. There's no ammonium ion in there. So there's no ammonia in there. So we'll write, in addition to this, this reaction, put a question mark after it, to indicate that we certainly recognize that this reaction must exist in this system, but is it a reaction of consequence in this system? Because ammonium ion reacting with carbonate ion is certainly a large extent reaction, and these reactions are each small extent at best. All right? So here we go. Q. Just so you don't forget our track. Is it reasonable to conclude that for this system, S equals calcium ion molarity, that we know for sure, also equals bicarb molarity, that we don't know about yet for sure, but we're operating on the basis that this is a possibility, which in turn equals the ammonia molarity. If this be true, we need only pay attention to this equilibrium reaction and the value for its equilibrium constant to calculate S. So, let's see what I get here. There's the equilibrium constant rewritten. This is guaranteed to be true. And if we take this to be true, then we get 7.2 times 10 to the minus 8, the equilibrium constant, is equal to S cubed over 1.0 minus S. Because the equilibrium molarity of ammonium ion will be its initial molarity less the equilibrium molarity of ammonia. And we are operating on the basis that the equilibrium molarity of ammonia is the same as S. All right? One equation, one unknown. We solve it for S. And this gives 4.2 times 10 to the minus 3 molar. Now we have a value for the solubility based on this as a possibility. What shall we do to find out if this solubility is correct? If this calculation has given us the correct solubility. Yep. We'll now analyze the system rigorously, which will take into account all the possible chemistry of the system. Knowing that if we do the charge balance, material balance analysis correctly, we got to get the right solubility.
Could you have done organic K constant where you
I didn't hear what you said.
could you have done what we did on Monday, where you looked at the ratio based off the pH of which of the different forms of carbonate you have? Whether you have carbonate or hydrogen carbonate?
We can't do that because we really don't know the system pH.
Okay.
Your question is a good one. But in order to do what you want us to do, which means get a ratio of HCO3 minus to hydrated CO2, because we know carbonate's gone, we need pH, and we don't have system pH. Well, let's go one step further with what we have on the board based on this solubility value, which is also then the molarity for bicarbene and the molarity for ammonia, based on what we've done so far. Can we now calculate system pH? Q. Well, rather than pH, we'll just say hydronium ion molarity. How do we do this? We got a couple acids in here who we can get a handle on. Bicarbene, ammonium ion. Ka, Kb, anything we want for system components. So I'll write this. By what we have done, have we got a value for ammonium ion molarity? We got a value for ammonia molarity? Well, we calculate hydronium ion molarity. Let's see what we get. Based on what we've done, this would give us the hydronium ion molarity. And what do I get? 1.3 times 10 to the minus 7. So, with this, if we wish, we can now get a bicarb to hydrated CO2 ratio. And if nothing else, answer the question based on the bicarb hydrated CO2 ratio we'd get from this. Answer the question about ammonium ion plus bicarb becoming hydrated CO2 and ammonia if it goes anyplace. But we now have enough information to go on with the true test of the validity of this analysis, which means we'll take the very same system and now subject it to the absolutely guaranteed to be correct analysis, which is material balance and charge balance. Remember we've said all along? When we get to the end of the pipeline in Chapter 18, you can now calculate correctly with equilibrium considerations at hand as well as material balance and charge balance. You can calculate correctly the molarities of anything in the system whose existence depends on pH. And that applies to this system, doesn't it? So, we'll write just so you keep track of what we're trying to do. Let's test these results by MB and CB analysis. Now, to get you prepared for Friday, I'm going to give you a reference to something. See? BQ2, because remember in the past I called special quizzes bonus quizzes, from summer 2011. And it's all available on Sakai. Okay? I'm telling you where to look. BQ2 from summer 2011. Now, one more directive. On BQ2 from summer 2011, this is question number 2. There's also a question number 1 on this BQ2, summer 2011. So I'll write on here, and consider both Q's 1 and 2. At a glance at the key, you'll see 2 is this. We're going to pursue this in class on Friday, as well as talk about question 1. So if you take a look at this before Friday, you'll be in good position to digest on the spot what we will be discussing.